Alright, in this video I'm just going to quickly go over the pre-test in the notes. I realize that some of you have done the wave standard last year and some of you haven't. So this will be new to some of you and this will be revision for others. Okay, so the first question asks us what the difference and similarity, first what the difference is between the sound wave produced by a loudspeaker and the light wave produced by a candle. And what we said was that the first difference, so firstly, let me just turn my pen on. Firstly, the sound wave or sound waves are longitudinal, and light waves are transverse. Sound waves travel at about 340 meters per second, and light waves at about 3 times 10 to the 8 meters per second. And sound waves are mechanical. Light waves are electromagnetic. Okay, so those are some of the differences. What we mean by mechanical, by the way, is that it actually requires a medium. Maybe we should add that as another difference. So, sound waves require a medium. Light waves can travel through a vacuum. Okay. In what way are the waves similar? Okay. The key here is that both of them are actually waves, and so they both do what waves do, which is both transmit energy without transfer of matter. Okay. State the definition of a wave. Well, that is the definition of a wave. So a means of energy transfer that does not require transfer of matter. Describe the difference between longitudinal and transverse waves. Okay. The difference is that a longitudinal wave, particles that make up the wave are displaced in a direction parallel to the direction that the wave is traveling. Transverse wave particles are displaced in a direction perpendicular to the direction that wave is traveling. Okay. Okay, now we want to label these things. So these things here is the way that the particle is moving. So in the transverse wave, we have the particle kind of moving up and down. So this is particle motion. So the source of the wave here, the hand, kind of moves up and down vertically while the wave travels horizontally. In this lower one, the hand kind of moves horizontally and causes a wave to travel horizontally as well. So in the bottom one, the motion of the particles that make up the wave is in the same direction or parallel to the direction that the wave is moving. So that means that this bottom one is a longitudinal wave. And this top one is a transverse wave. So now we've done those two. The wave velocity, we can just draw that in as an arrow representing the direction that the wave is traveling. So we can say wave velocity is that way. And in this case, we can also say the wave velocity is that way. So we've done those. The wavelength of a transverse wave is the distance between two consecutive crests or two consecutive troughs. So this is the wavelength. And the wavelength for a longitudinal wave is the distance between two consecutive compressions. So this is the wavelength. This is a compression here. And that's a compression there. Okay, so maybe we should add those. So compression and rarefaction, let's add those. Here we have a compression. And here we have a rarefaction. And then we want to add a crest and a trough. Those are properties those are points on a transverse wave. So this we call a crest. And this we call a trough. So a crest is the highest point on a transverse wave, and a trough is the lowest point on a transverse wave. And finally, we want to add the amplitude. The amplitude of a transverse wave, we can draw in a middle line here. Then the amplitude is the distance from that middle line to the crest, or the distance from that middle line to the bottom of a trough. So it's the furthest that the wave ever gets displaced. So these two arrows here, that one and that one, they represent the amplitude. Okay. Okay, this question has been cut off here. Describe these waves. What it really is asking is as longitudinal or transverse, as electromagnetic or mechanical. Yeah, I think that's it. So sound is a longitudinal mechanical wave. Whereas light is a transverse electromagnetic wave. Okay, so what we mean by that is that sound actually needs a medium to move through. It has to move through like a gas, a solid, or a liquid. Light can move through a vacuum, and it's really just vibrations in the electric and magnetic fields. We'll talk a bit more about what that means later. Okay, radio wave is like a special type of light wave. So a radio wave is exactly the same as light. So it's transverse and electromagnetic. The only difference between a radio wave and a light wave is that a radio wave has a longer wavelength. So it's identical in nature, it's just vibrations in the electric and magnetic fields. It can travel through a vacuum, but it's a longer wavelength. We can't actually see radio waves because our eyes aren't sensitive to that wavelength. A water wave is transverse, and of course it does require a medium, so it's mechanical. It actually needs to push on something to go. Okay. Write the wave equation. This equation is provided at the start of this notes. All of the equations for this topic are provided in the inside cover of your notes book. So write the wave equation. The wave equation is the one that goes V is equal to F lambda. And these quantities here, I'll just change color to red. F there is the frequency, or the number of waves that pass a point per second. Lambda is the wavelength, or the distance between two consecutive crests or troughs. And V is the wave speed, or the speed at which a crest kind of moves through space. Use the equation to explain what happens to the wavelength of a wave as the frequency increases. Okay, so let me go back to black. So if the wave speed remains constant, then F is equal to V over lambda. Or actually what I really want is to rearrange it for wavelength, because that's what we're interested in. So lambda is equal to V over F, which means that if we increase the frequency, which is in the denominator here, and V stays the same, then lambda gets smaller. So as F increases, lambda decreases. Write the equation linking period and frequency. So frequency is equal to 1 divided by time period. And we can understand this if we just say what each of those things mean. So the frequency is the number of waves that pass a point per second. The time period is the time that it takes, is how many seconds it takes for one wave to pass. So they're really just the inverse of each other. Frequency is the number of waves that pass a point in 1 second, whereas the time period is the number of seconds it takes for one wave to pass. So that's kind of summarized by this equation, where it says that F is equal to the inverse of the time period. Okay. So the diagram represents a wave traveling at 5 meters per second. Okay, so we know that the speed here, V equals 5 meters per second. Calculate the wavelength, amplitude, displacement, and amplitude of Z, frequency, and period. Okay, so the wavelength, I'm just going to move the whole board over a little bit so I can see the whole wave. Okay, so I think what we've got is this crest, this trough, and this crest, and the length of that adds up to 3 meters. So the distance between two crests is going to be 2 meters. We can also, the wavelength can also be the distance between this point and this point. That's lambda, which is 2 meters. Because that's 2/3 of the length. Okay, the amplitude is the distance between the middle line and the top of a crest. So this is the amplitude. A is equal to half of 1, right? So that's 0.5 meters. The displacement and amplitude of z, well, z looks like it's displaced from equilibrium about halfway to the top. So displacement at z is equal to 0.25. The amplitude of a wave, of a transverse traveling wave, is the same everywhere. The amplitude is defined as the maximum distance that any point gets away from the middle line. So the amplitude at z is also 0.5 meters. Because this point z at some later time will actually end up being up here, which means that the amplitude of the point z, which is going to be bouncing back and forth here like this, is going to be a, which is 0.5 meters. The frequency of this wave, well, how do we work that out? Do we know anything? We know the speed and we know the wavelength. So we know v is equal to f lambda. So f is equal to v over lambda, which is equal to 5 over 2, which is equal to 2.5. That's a frequency, so that's measured in hertz. Okay, hold on, we got one last thing to calculate. Yep. And that is the time period. Period is just equal to the inverse of the frequency, which is equal to 1 over 2.5, or 2 over 5, which is 0.4 seconds. Complete the labels of the diagram of the sound wave. Explain how sound is produced and propagates. Okay, so these two things here are rarefactions. These two things here are compressions. This distance here is lambda, the wavelength. Any other labels here? Okay, so what happens is the wave kind of travels this way, and the compressions and rarefactions alternately enter the ear here, which means that the eardrum gets pulled back and forth, which means that we register the sound wave in our ear and eventually in our brain. Okay, so how does sound propagate? The speaker vibrates adjacent sound particles, and then these collide and rebound off adjacent air particles, causing compressions and rarefactions. These compressions and rarefactions travel through the air to the ear. Okay, here we have an oscilloscope display of a sound wave. On the second axis, show a sound wave that is louder and twice the frequency. Okay, so louder means that the amplitude is bigger. That means that our eardrum is going to vibrate back and forth more, and higher frequency means that we get more waves per second, which means that our eardrum is going to vibrate more times per second, which we hear as a higher pitch. Okay, so basically the wave is going to be compressed horizontally and increased in height vertically. So I'll draw the same. I don't know what just happened there, but let's just go with it. So the key points are louder equals higher amplitude, which is the distance from that middle line to the top, and higher F is equal to more waves per second. So basically this is a time axis horizontally. So in this second wave that I've drawn, we get many more waves in the same time.